Before we get into p-n junction, let's talk about something important. Semiconductors. You have probably heard of energy levels in atoms, right? When we look at a single atom, the energy levels are neat and distinct, but things change when many atoms come together to form a solid crystal, like in a piece of silicon. Here, the individual energy levels of atoms start to overlap, forming what we call energy bands. There are mainly two energy bands we care about: the valence band, where electrons are still bound to atoms, and the conduction band, where electrons are free to move and conduct electricity. Now, depending on how these bands are positioned, a material behaves differently. In conductors like copper or gold, the valence band and conduction band overlap, so the electrons can easily move, and that's why they conduct so well. In insulators, the gap between these bands, called the band gap, is huge. So even if you try, the electrons can't easily jump from the valence band to the conduction band. But semiconductors sit right in between. At absolute zero, they behave like insulators. But as the temperature rises, some electrons gain enough energy to cross the band gap and move into the conduction band. And that's when the material starts to conduct. Two most common semiconductors are silicon and germanium. They each have 4 electrons in their outer shell and form a neat crystal lattice bonding with their neighbors. But here is the catch: pure silicon isn't a great conductor on its own, so we tweak it a bit using a process called doping. We add a small amount of another element called a dopant into the crystal and improve its conductivity. Now, let's say we top silicon with a pentavalent atom, something like phosphorus, which has 5 valence electrons. 4 of those electrons bond with the neighboring silicon atoms, but the fifth electron doesn't have anything to bond with, so it's left free. The free electron boosts conductivity, and we call this an n-type semiconductor. N4 negative charge carriers the electron, but there is another way. If we add a trivalent atom like boron, which has only 3 electrons in its outer shell, it bonds with 3 neighbors, but one bond is left incomplete. This incomplete bond creates a hole, a space where an electron should be. This gives us a p-type semiconductor, where holes act as charge carriers. Now, the energy band diagram of doped semiconductors is slightly different. In n-type semiconductor, the extra electrons from the donor atom have energy levels just below the conduction band, so they can easily jump up and conduct. In p-type semiconductors, the acceptor atoms have energy levels just above the valence band, making it easy for the electrons to jump and leave behind the holes. Okay, so what happens when we bring an n-type and p-type semiconductor together? We get a p-n junction, the basic building block of a diode. Now, we don't just glue them together. Instead, we take a single piece of semiconductor and dop one side with donor atoms and other side with acceptor atoms. This way, we avoid mismatches and imperfections that would mess with how the diode works. Now, let's look at what happens at the junction. There is a concentration difference. The n side has more free electrons and the p side has more holes. So the electrons from the n side naturally begin to diffuse into the p side, and the holes from the p side move towards the n side. But wait, holes are in particles, so how do they move? It's actually the electrons that are moving. An electron in the valence band jumps into a hole, leaving a new hole behind in its original position, and this keeps happening. So it's as if the holes are drifting to the other side. But this movement can't go on forever. As electrons and holes recombine at the junction, they leave behind immobile ions, negatively charged ions on the p side and positively charged ions on the n side. These ions don't move. They create an electric field, a kind of invisible wall. This region with no mobile carriers is called the depletion region or space charge region. It acts like a barrier, stopping further movement of electrons and holes. Now, let's look at the energy band diagram of a p-n junction. The conduction band and valence band are no longer flat. They bend at the junction. And the barrier formed in the middle is a potential barrier. For a carrier to move across the junction, it has to overcome this barrier. And that's where biasing comes in. Let's say we connect a battery to the junction with the positive terminal to the P side and the negative terminal to the N side. This is called forward bias. Now, the electric field from the battery opposes the electric field of the depletion region. This shrinks the depletion region, making it easier for electrons and holes to cross over. Electrons are pushed from the N side and holes are pushed from the P side, and current begins to flow. As we increase the voltage, the barrier becomes thinner and more carriers cross over. Eventually, the current rises rapidly. This is the exponential rise of the diode's IV curve. But what happens when we reverse the battery? This time, the positive terminal is connected to the N side and negative to the P side. Now, we are applying the reverse bias. Here, the battery's electric field adds to the junction's field, making the depletion region even wider. Electrons on the N side are pulled away and holes on the P side are pulled back, making it even harder for the carriers to cross the junction. So, does that mean no current at all flows? Actually, a tiny amount of current still flows. Where does it come from? It comes from the minority carriers, a few electrons on the P side and a few holes in the N side due to the thermal energy. These carriers get swept across the junction, but since they are so few, the reverse current is tiny, usually in microamperes. But here is the twist. If we keep increasing the reverse voltage, the electric field becomes strong enough to cause breakdown, suddenly allowing a large current to flow. This is the breakdown voltage of the diode. If uncontrolled, it can destroy the diode. But in Zener diodes, we use this behavior intentionally for voltage regulation. And that brings us to the beauty of PN junction. This simple structure, just one junction, can do so many things. It lets current pass in only one direction. It is used in rectifiers, signal detectors, voltage regulators, and even LEDs. It forms the foundation of transistors, solar cells, digital logic circuit. In the next video, we will explore how we build on this to create transistors, the real heroes of modern electronics. Thanks for watching and keep exploring the world of electronics.